Welcome everyone for our second day's first lecture. So we have Professor Courtney Schumacher with us, and Courtney kindly agreed to give a talk. It's way outside her working hours, and we also made her wait 10 more minutes. So we apologize for that. So yeah, Courtney will be talking about observed mesoscale convective systems in the tropics. Courtney, please take it away.
Great. Okay, I'm assuming you can you see my screen?
Yes, yes.
Great. Well, good morning, everybody. I am excited to be talking to your group. It looks like it's going to be a really interesting 2 weeks. Hopefully the first day started out well yesterday. And Bijut asked me to talk about observations of tropical clouds and MCSs. I think you'll be doing a lot more theoretical work or maybe more applied to different specific to the monsoon in particular, because that's the main focus of this workshop. But I'm really just going to be talking about the components, the different convective cloud types, and MCSs just in a very personal way, in the way I view them, and mostly through observations. And yes, so let's go ahead. Okay. Okay. So I was given the title Tropical Clouds. This is the only actual cloud image I'm going to show, but it's a really beautiful visible imagery from VIIRS, which is a low Earth orbit instrument on the SUMI NPP. And you can see a lot of complex, hopefully you can see my mouse, but just a lot of complex cloud structure in the tropics, where we have more organized ITCZ regions, kind of more pocketed stratocumulus regions, intense convective regions over the continents. And so we want to think about the clouds, that in particular, the convective cloud types in the tropics that contribute to this cloud field. And we want to know that because we're really interested in the rainfall that's associated with these cloud types. So this is, I really love this picture. It just shows, it's from iMerge, another satellite-based instrument product using mostly passive microwave, but some other infrared and other sensors as a blend, but it's a pretty good product for rainfall across the tropics. And you can definitely see that where we saw more cloudiness, we tend to have more rain, but a lot of complex structure around coast here in India. You have really some strong coastal rainfall, and obviously during the monsoon, this would look a lot different. This is just an annual mean. And so then we want to kind of get at what is the cloud, the convective cloud types and that are producing this and why. So let's talk about the cumulus cloud types. Again, pictures, photographs are like, it's really great to just go out. Best observations are your own eyes. So go out and look at clouds, and hopefully you see a lot of these when you go out. So I have some simple ones first. Fair weather cumulus. They're typically not very tall, and they are not precipitating either. When they start getting to about 1.5, 2 kilometers, then they'll start creating precipitation-sized particles. Cumulus congestus are things that start growing a couple kilometers, even up to the 6 kilometers, which is above the 0 degrees Celsius level. So maybe a little glaciation at the top. And these are associated, you can see, with precipitation at the bottom. So often when I look at clouds, I also want to think about why they're doing what they're doing. And so I just thought maybe we can have a quick little view of cumulus dynamics in terms of a historical viewpoint. And so people are sort of like, how, because you're going to be talking about how do we get at these kind of cumulus processes or these convective processes in theory and models. And so these are also observations in labs where people did like steady state jets back in the 50s, and they realized, well, gets us kind of close to the cauliflower growth of a convective cell, but it certainly just grows too fast. And then the next year score said, well, let's think about convection more as a thermal bubble. And so you can see this is with time and it's going down, but it also kind of has that look of these convective clouds, but it's too diffuse. So where the steady state jet was too strong, this thermal bubble is too diffuse. And then into the 60s, people started combining those. They started taking the jet and capping it with a thermal. And so for a long time, the starting plume, or this jet capped by a thermal, was a really a popular way to think about convection. And you can see here, this is really, again, a nice lab view of where you can think about the entrainment that's happening. You can think of this as an updraft in the entrainment at the side of the cloud and at the top. And then most recently, Hugh Morrison and colleagues have been talking about something a little bit, something in between a thermal bubble and a starting plume, where you have thermal chains, where it's an intermediate, where you have a series of starting plumes, basically. And so there's just a really rich literature out there about why these clouds grow the way they do from a dynamic standpoint. But when in doubt, go just look at the cloud and try to measure it. And if I have a time lapse on my computer, but I didn't think to bring it up until just now. Okay, so those are then there's yet another. If you know your clouds, you would know that I left out cumulonimbus in that discussion so far. And this is when these are really tall cells here. This is a life cycle. This is a picture of one, but here on the right is this is Regnault and Hobbs. They took the schematic was from like 90 different flights of cumulonimbus, of isolated cumulonimbus. And so this is supposed to be a life cycle of where if you start with a strong updraft that then glaciates and then rains out. And this is all about an hour. And so that's the kind of the building block or of a convective system is going to be the life cycle of this single cell. And these cells are, whereas the others might have been 1 or 2 kilometers, these are getting to widths on the order of 10 kilometers. They can extend vertically to the tropopods. They don't have to, but they definitely need to be above the 0 degrees Celsius level to be considered a cumulonimbus. And then when it does hit the tropopods, you can spread out and get this characteristic anvil. We care about these cumulonimbus because they precipitate heavily. They often exhibit lightning, so you have to have that mixed phase region for the lightning to be able to form, for the charge separation. Of course, at the surface, there can be strong outflow winds. So these are very impactful storms. And I'm a radar meteorologist, so I look at convection with radars often, and I want to explain a little bit why that they're such a useful tool. So if you're not familiar with radar, it's an active sensor that sends out microwave radiation and listens back for it. And here, this is in Darwin, Australia. These are the Tiwi Islands, and where there's the brighter colors, that means you're getting reflection back both from the number of particles, but the size of the particles. And these types of radars only see rain. They won't see the fair weather cumulus. They won't see this very shallow non-raining cumulus. And so here, they call this Hector, and I'll take what this looks like. It's Hector because during the day over these islands, you get these very regular convection, and they call it Hector. And people like pilots can track their path in nearby using the regularity of these convective cells. And so these are cumulonimbus in different stages of development. Here's a more mature one, and these ones are growing. So if you take a cross section where this magenta line is through those 3 or multiple cumulonimbus, this is what the radar is going to see. And so it gets a 3-dimensional view of the radar. So this was up near the surface, or about 2.5 kilometers, not quite the surface. And here, this is in the vertical. You can see it with height. And so this is the very tall strong cell, and these cells are not quite, they're still growing, and they're not quite as high, but they're starting to grow and glaciate. And so this is sort of, the radar is it's kind of like an X-ray of these systems. And so I will be showing you quite a bit of radar data in the rest of the talk. And then I want to point out, again, I've been talking more about isolated convection, but here, can you kind of see, hopefully, yeah, I wish I could be there seeing you guys. Yeah, I can. Oh, look, I have the camera now, so I can kind of see you. By the way, if you have questions along the way, you can, or I can try to save time at the end. You can ask via the microphone. But anyway, I took the circle around there's two grouped together. And so what happens, these systems don't stay individual for very long. And a lot of times you'll get them grouping together, and then they'll start the formation of one will help form another one, and then they'll be in different stages of development. So here's a multi-cell thunderstorm, which is, I think, a good example right here, where here's a more mature one, and this one is still growing. And if these are each about 10 kilometers, you can get cells that are on more like 30 or 40 kilometers, or thunderstorm systems. Okay, so those are our three main convective cloud types that we often talk about in tropical meteorology and observations of those. And so there's a very, hopefully some of you have heard of this. It's the trimodal distribution of convective clouds. It's a very famous paper by Dick Johnson and colleagues from 1999 that they took a lot of observations from radar, from just going out, being on ships, like during Toga Core, for example, in the West Pacific. And what they show here is it's the number of cells. For here, they have the number of cells on the y-axis. And so these are the cumulus ones. Those are the tiny little ones. They're kind of everywhere. And then here on the other side, and then the same with the sizes. These are 10 clouds versus 1 cloud. So what some are, yeah, these are just different distributions. There's a lot of kind of more shallow clouds. There's a lot fewer of the cumulonimbus. And so this is why they put it by the percent of convective. Yeah, here are the congestus. So you have a lot fewer congestus with higher tops, echo top heights or cloud feature heights. The percent of convective rainfall from cumulonimbus, they don't have the number, but rather the percent of rainfall, because they don't happen very often, but they do cause a lot of the rain. But what was important about this study was that most of the time people just thought of shallow non-raining clouds and big cumulonimbus. And so it really brought out the importance of the congestus, this mid-level convection. And then they even made a schematic that's also very famous, where they took the geographical distribution of this trimodal distribution and showed that you tend to get a lot of this is latitude on the x-axis. But here, these are the tau convective towers, or where in the ITCZ. And then on the edges, so in the ITCZ, but on the edges, you get the cumulus congestus, and then even some of the shallow raining stuff that just grew tall enough to rain. But as you go further away from the ITCZ, you get much more shallow clouds that are not raining. And so these very distinct cloud types are driven by in part by the atmosphere. So where you have the trade inversion at 2 kilometers, a stable layer at the 0 degrees Celsius level, and then of course the tropopause as stable layers that are creating these distinct, this distinct trimodal distribution. So I'm going to talk a little bit more about this radar, because I'll be showing you a lot of images. This is radar in space. So hopefully some of you are familiar with TRIM and GPM. It's a NASA Japanese joint mission. And it's provided decades of observations across the globe of a number of instruments. And the one I'll be focusing on is the radars, the PR and the DPRs. And so they are KU, but they both have KU band radars. So it's about 2 centimeters. They have a precessing orbit, so they observe the full diurnal cycle. With time, it takes a while to sample that. And those are the frequencies. And again, it can get you that vertical structure and the horizontal structure to help us define the rain into different types. And so, but we can get this near globally. We have higher latitude range with GPM, but the tropics and subtropics with TRIM in the yellow. So this is taking, I'm just looking at GPM data, so the one that goes to higher latitudes. And so this is all rain that's shallow. So this is less than 0 degrees Celsius for the echo top height. And this is the deep convective distribution. So we can go ahead and say, where are these cloud types happening? Where are these convective cloud types happening? And hopefully you see most of the shallow convection happens over the ocean and the warm ocean, where there's upwelling regions, there's really not a lot of convection, deep or shallow. But there's very little over land. And so just note that. Whereas the deep convection and the shallow convection is about 3 to 4% over the tropical ocean. That's sort of averaged over the year. But you can imagine convection doesn't cover that much area. It can't. And then deep convection, it's both over the ocean and over land. So we see these nice ITCZ features. And then you get a lot of deep convection over hotspots like the Amazon, Congo, the maritime continent. Even some interesting features over the Indian subcontinent. Deep convection, again, is even less area, 1 to 2%. So it's just not, it just physically you can't, because you just can't cover a lot of area with convection based on the strong updrafts and then the subsidence outside of it. So I'm going to bring this picture back. And I wanted to point out that this trimodal concept really applies only over the tropical oceans. We don't get a lot of this. I mean, this is all rain. We can't see any of this shallow non-raining cloud. But basically we don't have a very robust congested population over land. It actually just rapidly grows from shallow to deep during the daytime. Whereas over ocean, you have a much weaker diurnal cycle and you can have a more stable congested population. So I just want to warn people, I see that people do this a lot where they bring up the trimodal concept for over land and ocean, and it kind of breaks down over land. But what's really especially interesting is the intensity of the convection. And so this is from the TRIM radar, which was up before the GPM radar. Again, radar from space. And this is just there's a precipitation feature database that I highly recommend if you want to look at different features of these that have been grouped into systems. Of things like overshooting top, so greater than 14 kilometers. So this is when the radar sees things that go above the tropopause. And you can see most of those, the most extreme ones, happen over land. The same thing, the maximum height of the 40 dBz echo. That means you have really big hydrometeors very high up. And again, those intense storms happen over the tropics, again, Indian subcontinent. I'm sure this is happening. Well, I'd be curious. I don't know about the season. I have to look back at the seasonal distribution and how that relates to what's happening during the monsoon or not. But certainly land is when you get the most intense deep convection. Whereas over ocean, you get a more moderate convection and a lot more congestus. Okay. So now I get to transition. You're like, why hasn't she talked about, I've been talking for 20 minutes or something. I haven't talked about the MCS yet. Okay, so I just wanted to prep us now to let's just start with talking about convective organization. So these are old, so, I have to admit, I took a lot of these slides from old notes and old talks I've given, and I do like going back to old slides because these are things we've been thinking about for a long time.
She was there for a while. I think she stopped sharing. Can admin check if it is a problem at our end or?
No, I think it's, I'm at a hotel. Can you hear me?
Yes.
Okay.
Hi, Courtney. This is Vishal. Vidyut is just besides me.
Oh, okay.
Yeah.
When did you lose me?
When you said that sometimes you like bringing up old slides because.
Oh, yeah, this is it. Okay, I'm good. Okay.
Thanks.
I apologize. I'm pretty sure that was my internet. Can you hear me?
Yes, we hear you well.
Okay, great. Okay, and you can see?
Yes.
Yeah. Okay, awesome. Okay, back to my old slides. Okay, so these are radar observations over the Caribbean. And so again, anywhere there's dark is where there's echo that's raining, or clouds that are raining. And you can see that there's a lot of scattered showers. And this is over the whole Caribbean, so it's over a really large region. And there's just kind of scattered showers everywhere. Here on this day, there seems to be more. They're still scattered, but they're kind of bigger cells. And then here we're starting to get things that are starting to like organize a bit, I would say. Or they're kind of looking a little bit less like this and a little bit, kind of a little more clumped together. And then you have days that look like this, where there's just really a lot going on. And I want to point this out. This is something, the log normal distribution of precipitation of precipitating cells is something that Lopez and many others have pointed out. So you get a lot of little cells and fewer big cells. And that's certainly the case with convective cells. So then I want to focus, then, you know, I'd say the extreme here is sort of like what's going on there, what's happening there versus here. Okay, so I don't know. This is where I'd be like walking around and trying to talk to you guys and be like, what do you think? How do you define radiation? But I'll go on. I'll give you some ideas. If you think, well, what does it mean? How am I going to define convective organization? Is it the shape? Is it something that's linear? Some people say that. Could it be a lifetime? Something that oh, my connection is unstable again. I might take, well, hopefully it'll keep on going. Like it could be lifetime, something that lasts a long time, much longer than in an individual cell. It could be the area of a system, something that's really big. So we saw instances of the shed linear shapes. We saw things that were big. And here's when I'm going to first define an MCS, which is going to be something that's going to be greater than 100 kilometers of precipitation in horizontal extent. This is from Bob House's definition, but it's something that I use quite a bit. There's also, you probably hear about this during your time, the indices of aggregation over a grid box, right? I just listed two, there are many out there. So these are just some different ways that people define convective organization. Again, I was told to talk about this, but I believe strongly in the importance of mesoscale convective systems as an important type of convective organization. So that's the rest of my talk will be about convective, about MCSs basically. So MCSs, they're not just convection. Most of them contain also what we call stratiform rain. So this is, again, that same Darwin radar covering a much bigger area than just the Tiwi Islands. This is huge area. It's covering, it's got, if you take the vertical cross section through here, you have deep convective cells that you may hopefully look familiar to you. But then we have this really large horizontally homogeneous area of rainfall. Here, this is 0 degrees Celsius level to indicate the height that normally is about 5 kilometers. And so if we take a schematic of that, this is going to be something, again, greater than 100 kilometers. It's got deep convection, and then it's got this big stratiform area that's fed by the deep convection. And within both of these regions, they're so important because this is what causes the big systems, but they're different. They're very distinct dynamics and microphysics that happen in here. This is just showing the dynamics of the updrafts and downdrafts in the convective region with different types of vertical motion and cloud structures in the stratiform region that then can anvil out. I'm going to talk only the tiniest bit about anvil. I'm not sure how much you guys are going to cover it in the next 2 weeks, but this is something that these MCSs can create a large amount of anvil. Just because I'm an observationalist, I don't want you to show you how these things might vary. This is from a spaceborne radar, and here is the leading line and trailing stratiform region. These are horizontal cross sections. These are vertical cross sections. And again, this should look up kind of what I just showed you, the convective cell here in the leading line, the big stratiform region, what we call a bright band around the 0 degrees Celsius level, covering hundreds of kilometers. This is what we call the classic leading line trailing stratiform. This is another thing people don't talk about very much, is that how messy over the ocean that MCSs can be. And you might look at this. This is a horizontal cross section. And this is a couple hundred kilometers across. This is the swath of the radar. And you're like, well, that doesn't look like an MCS. Well, if you take the cross section, you can see, well, we've got 200 kilometers of a continuous rainfall. So, and it's really mostly stratiform from aged convective cells. So this is a lot of MCSs over the tropical oceans look like this. Not all of them many of them don't look like this. So just keep that in mind. I threw this in here because I think these spaceborne radars are really nice for looking at regions of topography, which many of you are familiar with. You live in a place of amazing topography, and you can get different convective organization depending just on how the large scale flow interacts with the topography. So you can get big MCSs over the foothills. You can get just more multicellular or less stratiform systems when the large scale flow changes, and then things over the Tibetan Plateau can also change. So I just wanted to point that out. There's just a lot of applications, more regional applications you can use the radar data for. And the kind of using these same building blocks I've been talking about, these convective and these shallow and deep convection, and then the stratiform rain, to understand the precipitation processes and storm structures over a region. This is a blow up. I had shown you a schematic with the vertical motions, and I'll get back to those in a little bit, but I wanted to say these vertical motions go along with very particular microphysics. So if any of you are getting into, it's not just the convective dynamics, but in here where we have the strong updrafts and the convection, you have growth by collision and coalescence. So this is where you can get really large drop formation and these really strong updrafts. There's transport, these regions communicate. So there is transport over into the stratiform region where things tend to fall, and then they start growth in this weaker mesoscale region. These are, I know it looks like a big arrow, but it's actually weaker vertical air motions. It's going to be deposition aloft. They melt. Once those snowflakes fall, and they start melting around the 0 degrees Celsius level. That's where we get our radar bright band, and that's the cloud base. So whereas the convective cloud base is much lower, like 1 or 2 kilometers, the stratiform cloud base is around the 0 degrees Celsius, around that 5 kilometers. And so then we have evaporation below the cloud base, and then you get a mesoscale downdraft. So these very distinct kinematics and microphysics really change the way these systems evolve and communicate. And like I said, I wanted to give you some quantification of what the vertical motion is, like how strong is the vertical motion in a convective cell. This is over Darwin. These are vertically pointing radar retrievals. And this is, the left here is, and this is just the reflectivity of what that might look like from a profiler, just looking straight up. And these lines show going from shallow, mid-level, and deep. This is the mean vertical motion that was observed. So you can see that as things get stronger, you might have 1 meter per second for shallow convection. You might have more like 2 meters per second in deep and the cumulus congestus, and then 5, 10, 15 meters per second in the deep convection. The stratiform regions are a lot weaker, where you only have less than, less than 3.3 meters per second and any of the stratiform regions. And then you actually have downward motion below that negative, where the evaporation is happening. And for those of you interested in ANVIL, this is a tidbit. We can do the same thing. We can look at if there's big enough particles to be seen in the ANVIL. We can see some dynamically active regions in these these places where there's not rain reaching the surface. Again, the motions are very weak, and there's some evaporation below the cloud base here. But this could be associated with radiative processes or even gravity waves. The MCS has a life cycle. It doesn't just pop up as this really big thing that covers hundreds of kilometers of rain. You have to have convection. No matter what, you will not get an MCS or in the tropics or large amounts of rain without the convection. So you have formative isolated cells. Then when they start growing together, becoming multicellular and intensify, the cells merge, they intensify. And then things are mature when the stratiform region has some of these convective cells have decayed or provided material over to the stratiform region, and the stratiform the mesoscale updraft has begun. So you have your mesoscale rain region forms. That's when we have our most robust MCS. And then the dissipating, it's when the convection stops forming and you're just left with the decaying stratiform. And this whole process took 6 hours, 12 hours. Some MCSs can last up to a day or so. So this is, again, many hours of a life cycle. And this matters. This is how we get so much rain from them, right? So this is Churchill and Howe's. This is, I think, MCS over Indonesia, but this is with time on the x-axis. And this is here, it's the area. So the beginning that, your convection kicks off, and then it kind of stabilizes. So it's kind of there. It's, you got convection going. And then you have the stratiform region start really picking up. So that's the mature phase here. And so the stratiform rain in the whole life cycle of the MCS covers is a lot much more area than the convective rain. So it has more of a radiative impact as well. If you look down here, this is the rain rate. So there's most of the rain is convective earlier in the life cycle, but later on in the life cycle, the stratiform rain becomes dominant. And so almost half of the rain in the tropics and from MCSs is from the stratiform part. So you can't just study convective dynamics and understand an MCS, because then you would be ignoring what's happening in the stratiform region. These MCS sizes also are logarithmic. Here, this is over the West Pacific. This is accumulated frequency on a log scale on the x-axis, and then cloud shield size on the y-axis. And if you say, let's look at the 1%, frequency, so rare, doesn't happen very often. They're pretty big, right? So the big ones don't happen very often. The little ones happen a lot more often. But if you look at the contribution to cloud cover, so cloud shield size is now over here. So this is the same 10 to the 5th over here that I said only happens 1% of the time. It accounts for on the order, depending on your infrared brightness temperature threshold. These are all pretty cold cloud tops, about 50% of the cloud cover. So even they don't happen very much, they have really large impact in terms of cloud cover and also thus rain. Okay, so hopefully I'm not going too fast, but I wanted to get at, now that's describing the kind of phenomenology of those, of the different cloud, the shallow convection, the deep convection, and the stratiform. And then I wanted to this is just one slide to get you thinking about why things might organize, what matters, if you want to get convection to organize in your model, what are some of the things you need to be thinking about? This is mostly observationally based. Some of it has been helped through models, but I've been trying to stay true to my observational background. So first, you have to initiate the convection and maintain it. Otherwise, the system dies off. It's the food for the storm. So what is convection like? It likes warm, moist boundary layers. It likes when things, a little bit of shear at low levels, not too much. It likes downdrafts and cold pools because that helps form new convection. So here, this is my little downdraft, my cold pool here. And then other synoptic and mesoscale boundaries. So anything to lift that air up and to start the updraft, start the buoyant release of energy. So then once that convection is going, things are happy, you need to move on if you want to think about what might make an MCS form and maintain itself and create anvil. You have to really be looking at the mid and upper level moisture, because that's where most of the cloud is. Mid and upper level shear and advection, this is hydrometeor advection from the convective region, and shear, that's going to affect how thick that cloud is, how far it spreads. Gravity waves. So the convection convection can act, it's like you throw a rock in a pond and the ripples go out. So this is what convection is doing to the atmosphere. The convection, then you have the strong updraft. It displaces mass that then causes these ripples in the atmosphere. And this is what these are supposed to be. These are supposed to represent sort of gravity waves in the stratiform region that can kind of then help kickstart some of those depositional growth processes. And then the radiative feedbacks can definitely impact, especially anvil, but the stratiform cloud as well. So these are different things you can think about that to make something realistic in a model world or a theory world. These are things you kind of have to think about. And then the last bit of my talk is going to be how MCSs affect other things. So here I've talked about the different cloud types, very briefly what they like in terms of the environment, and then how do they affect the environment. So here I'm going to invoke a concept called the apparent heat source, popularized by Yanai et al. In 1973. And this is just saying this is the heating that you get from unresolved diabatic processes in the atmosphere. Those unresolved diabatic processes are the radiative heating or cooling, latent heating or cooling, and then eddy sensible heat transport. And so this is, you can measure it. This is different ways, again, observationally measure it. These are red dots or soundings. So you can do a sounding based budget to get at this, the Q1, this apparent heat source, or you can measure these different components using things like radars and soundings to get at these different components to get at the total Q1. So I'm using the sounding based method here. So all of these are observed profiles of at least retrieved from a budget, from a sounding budget of apparent heating, this Q1, for different cloud types. So here's our fair weather cumulus, our cumulus congestus, our cumulonimbus. These are really pretty pictures from Art Rangno. He's a great photographer. And so the heating here, I'm going to start with the fair weather cumulus. Oh yeah, and these we use synoptic. I don't know if any of you have gone out and looked at convective cloud obs and had to do the WMO classification of low level clouds, mid level clouds, or if it's CL1, it's low level, or it's a cumulus congestus with low base. If it's CL3 or 9, that's a cumulonimbus. CL7, that's going to be the MCS category. So you can see that the fair weather cumulus have low level heating and then cooling through the rest of the troposphere. Whereas as the cloud deepens, you get more heating, that deepens with the height of the cloud, but then there's still cooling at the cloud top, or this could be, some of this is evaporative and some of it is radiative cooling, and we can't really separate it out with the budget analysis. The cumulonimbus, they're much deeper and stronger, they rain more, so they have deeper heating throughout the depth of the tropopause, troposphere, except maybe a little bit of cooling below cloud base here, and a very high amount of heating compared to the K per day over in the shallower clouds. The MCSs, because they're so big, they rain so much, they have elevated heating here. And because of the cooling that's happening from the evaporation below, and really much bigger magnitude. And so this is sort of how the atmosphere feels these MCSs through this heating. I think I'll skip. I have something about the moistening. I'm going to skip that I think I'd rather have questions at the end. This heating has implications for the large scale circulation. So this was a study done long ago by Hartman, but I redid it for my PhD work. But if you took the heating, hopefully that looks like that cumulonimbus heating to you. We go back. See, this is our cumulonimbus heating with the mid-tropospheric maximum, and then you have more of this elevated heating with a higher maximum in the MCS. Okay, so they took kind of these idealized profiles and plugged them into a GCM, a dry GCM. And this is where if you just used the convective profile, this is what the Walker circulation would look like over the Pacific Ocean. So kind of up and down stream function anomalies here. Whereas if you put in the MCS one, you actually get the whole large scale. The Walker circulation looks different. The circulation actually tilts. And I'm not showing it, but it's actually more realistic based on reanalysis. The other thing about these MCSs is that they can act as a prototype. So I've just talked about things that go from kind of shallow to mid-level, to deep to stratiform. Here in these MCSs, here you have the mid-level deep stratiform. Here you have the shallow, mid-level deep stratiform. And these are these MCSs that last on the order of a day or less. But you can also see the same thing if you look at larger scale wave structures like 2-day waves or Kelvin waves, things that last 2 to 5 days. You have a whole day of shallow, a whole day of deep, and then a whole day of stratiform. So you stretch out that MCS life cycle, or the relative proportions of those cloud types over 2 days or even 3 to 5 days. You even see this for the Madden-Julian oscillation. This idea over weeks, where you have relatively more shallow clouds or relatively more mid-level clouds or relatively more deep or relatively more stratiform. And so this, Brian Mapes came up with this idea, George Kouladis and others, this idea of these stretch building blocks, or that this is a prototype of wave interactions, convective wave interactions. So in that, again, you have to understand the cloud population and how they evolve with their external forcings. This is something, of course, then I need to bring it back to rain. This idea of this is when you have big organized systems, they rain a lot. And so these are actually tracked MCSs. Steve Nesbitt did this first, but Russ Schumacher, that's not me, it's a different Russ Schumacher, and Kristen Rasmussen updated this. And so anywhere it's sort of there's red, this is showing like this is 75% of the rain comes from MCSs here over West Africa. Over 50% in the, over the ITCZ. This is interesting. So yeah, again, India, it's fun to look at these in more detail. I'm sure this changes with the monsoon and the phases within the monsoon, but certainly some variability there spatially in the annual average, how MCSs contribute to rain in a region. So this is we care a lot because MCSs cause a lot of rain. I think I have just one or two more slides, then that way I can leave some time for questions. Yes, I have two more slides. I'm coming back to the GPM radar to show that it's not just it's the MCSs themselves, but again, if you want to break it down onto these components, we have our shallow convective, our deep convective. I've already shown these maps. I really wanted to show what the stratiform looks like from the radar. And hopefully you can tell there's a lot more, again, it covers more area. It doesn't have the same dynamical constraints that convection does to have subsidence in between these strong updrafts. And then it's coincident with the deep convection of the tropics. So anywhere we see deep convection, we see stratiform rain. Okay, so this is so important. The deep convection spawns stratiform rain in most of the tropics. The rain that we see in the extratropics, yeah, I'll come back to that in a second. So if you actually take the amount of rain that's from stratiform globally, I had mentioned it briefly on one of my previous slides, but if you look globally, these reds or magentas are like 50% of the rain. So on the order, almost half of the rain in the tropics comes from stratiform rain. And again, it depends on where you're at. Less so when there's the colder SST regions are on the edge of the ITCZ. Once you get into the higher latitudes, you don't have nearly as much deep convection. You have a lot more stratiform rain. It's a different type of convection there. These can also be these are more extratropically driven by like large scale fronts, baroclinic lifting and things like that. So they're kind of different beasts than the kind of MCSs and the stratiform rain that forms in the deep tropics. My last results per se, again, these are all personal views. There's so many observations of convection and MCSs out there, but I wanted to talk about the diurnal variability of these different rain types. I think we all know that the diurnal cycle varies if you over land and ocean, but it also depends on what cloud type you have. So for example, this is the time of maximum rainfall for shallow convection, deep convection, and stratiform rain observed by the GPM radar. The blues are the early morning, greens are later morning, yellows are early afternoon, and then these kind of reds get into a later afternoon, early evening. So over the tropical oceans, the shallow convection is in the morning. And then over land, it tends to be early afternoon, although that depends over the Amazon versus Africa versus even the Indonesian subcontinent. Like there is variability on when the timing of the shallow convection happens. When you get into the deep convection, it happens later in the day. Certainly over the ocean, it's not as clear as a signal. There's a weaker diurnal cycle over the ocean, but over land, we see these darker reds. Things are, the convection is evolving into deep, going from shallow to deep in the late afternoon and early evening. And again, there's some nice structures. Sometimes you see some rainbow colors or some other colors, and that could indicate propagation. Like the Himalayas, there's some really nice, can you guys see that's more blue? So there's certainly some interesting orographic forcing and kind of in propagation that you can see in this image. And then finally, the stratiform rain, again, it's a little bit messier over the ocean. It's a weaker diurnal cycle. But you see things are starting to get into the magentas, and these are going into pinks and purples. So those are going into the like late evening and early morning hours. And so the stratiform, that cycle is extended out well past your typical daytime maximum that you think of for deep convection. And so to finally to put this in a sort of a compact way, over land, this is just over the tropics. This is the occurrence. This is a percent from the mean. So sorry, these are very small. But inside the circle, it's shallow, and then as you go further outside the circle, it goes to deeper and then stratiform rain. And then noon, I'm sorry, this is probably too small for you guys. I meant to put this font bigger, but this is noon here and midnight here. So this is saying over land, you get your shallow convection that starts around noon. It starts growing throughout the day. And you really get your deepest convection around, this is between noon and 6, so the late afternoon. And the stratiform, you can see the stratiform really extends out throughout the diurnal cycle. So when you get these are your big MCSs that can last long, that can overcome the diurnal cycle, the daytime diurnal cycle, and have their own kind of evolution into the evening hours. This is midnight, 6 a.m. This is sort of the most extreme stratiform rain that we have. Whereas the ocean, again, this is still all the same cloud types and the noon and midnight. So here's noon, here's midnight. So you can see that early morning is when the shallow happens, and then it doesn't quite cycle as much, but everything's sort of happening in the early morning. As you get deeper, you tend to this is 6 a.m., so things can start happening in the later morning. And then anything over the ocean that's going to be long lasting is going to be something that has a lot of stratiform rain. It's the MCS again, overcoming the nocturnal life cycle over ocean. So I don't have a proper conclusion slide. I just thought I'd throw this up. I normally show the schematic all the time because this is, again, an old schematic from Bob Howes, but I really love it. That shows you have your shallow non-precipitating convection. This is your fair weather cumulus. Then you have your deeper congestus that's raining. Then you have your very deep convection that's raining even harder and has stronger vertical motions and microphysical processes. And then you have your big stratiform anvil region with the mesoscale updraft and downdraft. So these, and then that we know this, there's some theory behind it, but also we know because we observe this. And radar is a really great tool to look at these different cloud types and how they can either act in isolation or act together to form MCSs that have significant impacts on the large scale circulation and precipitation climatology. So you've got to be thinking about why they do what they do and what the impact of that. So with that, I will stop sharing. And I think I left time for questions.
Yeah, Courtney, you have good amount of time, I guess.
Well, you guys started late because of coffee, but which is great. You should have coffee.
Okay, do you have any questions?
Yeah. Thanks. That was a great talk. So in one slide, you were showing about the shallow convective precipitation dominating over the oceans compared to the land. Is that kind of attributable to the stable subtropical highs over the oceans, which is not found over the land? Maybe a stronger trade inversion where in the regions where there is no upwelling. Could that be a reason for more?
Yeah,
shallow?
absolutely. Yeah. Oh, yeah, for sure. The trade, this is the ITCZ, but a lot of these other regions outside of that is more strongly here, like impacted by the trade inversion for sure. And then overland, you don't get you don't get the trade inversion. And I also think the diurnal, coming back to the diurnal cycle. Yeah, so I think the subtropical highs, well, the subtropical highs might have a little bit to do with it, but I think it's more, these are warm SST cloud types. They're really not going to be very prevalent over the subtropical high regions if it's pretty cool. If things are, there's a really large amount of descent. Whereas the trade wind inversion, there's still a lot of bubbling warm ocean underneath the trade wind inversion. So yeah, I think you're exactly right. There's just stronger trade wind inversion, and then you have a less strong diurnal cycle, so that things can kind of sit around and be shallow and not forced to grow.
And one more question is regarding the heating rates that you had showed for stratiform. It was close to 15 Kelvin per day is what I remember.
Yes.
So in that case, if these MCSs are found in a background where there is no background circulation existing prior to the convection, what time scale, like what could be the time scale that a forced circulation can be generated with the given heating from the MCS, like when there's no background Kelvin wave or something?
Oh, that's a great question. You mean in the environment?
Yeah.
Yeah. So, I normally think of this in gravity waves. So it's these gravity waves spread out because the heating is forcing a gravity wave response. And the convective gravity waves can move quite fast. 30 to 50 meters per second. Or maybe those are 50 meters per second, and the stratiform are slower, more like 30 meters per second. And so those will spread out pretty quickly. And I think of the gravity waves like coastal gravity waves, that when we see this, we're definitely looking for things like 15, 20 meters per second from heating impacts. So that time scale, you can just, however long you want to propagate that out for. So over hours.
Okay, thank you.
Great. Good questions. Thank you. I see Jagdish has one online. I have the chat up if.
Yeah. Can you hear me?
Yes.
Yes. So I'm attending this session online. I'm a PhD scholar in IITM. So I have few doubts. So in your definition of convective organization, actually in literature, there are many definitions. So what reasoning I should follow to choose the best one?
I don't know if there's a best one. It's what you're interested in. So I pick MCSs. And the one I use for MCS is the scale, the spatial scale of it, because I'm interested in rainfall and heating.
Okay.
So if you have sometimes people might be interested in fast-moving linear features because they're more damaging. Some people might be interested in the longer lasting ones because of the radiative impacts, which area would also feed into. You're going to hear more about some of these more idealized aggregation statistics. What does it mean? For maybe might be the same amount of rain, but things are scattered throughout versus one big clump. And what does that mean to the large scale circulation or to whatever you might be looking at? So you should have doubts, but you should also be aware of what metric you will answer the question you're asking.
So I have another doubt. If you see the stratiform profile, that vertical velocity profile, actually I have always this doubt. Why there is an updraft above the melting layer? It is due to latent heat release or something else?
In the stratiform region?
Yeah.
Let's
That
see.
peculiar curve.
I will get there. Okay.
Yes, like that.
So in the stratiform region.
Yeah.
So what this overlap? Oh, these are just different. This is robust. I'm sorry. These are just different types of stratiform. So
Yes.
I didn't explain that very in detail. So this is when you have really robust, like strong rain, and then you kind of have stronger updrafts. This is when you have weaker rain and kind of weaker cloud structure and a weaker bright band. So these are transitioning over. This is right when the melting is starting to happen. So you're getting cooling from melting. This line is around 5 kilometers, which is the 0 degrees Celsius level. Yeah, and here you have this rapid melting and then just evaporation here. Was that your question?
No. My question is why there is an updraft above this melting layer, like 4.5
Oh, what's
kilometers.
here?
Yeah,
Oh,
yes.
I
Yes,
love,
yes, yes.
yeah, I love that because there's deposition. Oh, here we go. Because there's growth. So I'm going to invoke, I like gravity waves a lot. And so I think what starts off the growth here is the gravity wave. So the convection is detraining material, hydrometeors over, this could just be detrainment. But there's also gravity waves that are forced, that are kind of causing more upward than downward motion in here. And then you start getting the depositional processes, which adds extra latent heating, right?
Okay.
So things aren't just falling. You have gravity waves forcing things up, creating latent heating. And so then it's a self-sustaining process where the heating is causing growth. And then there's also an argument that you can have radiative processes here where you might have cooling at cloud top and warming at cloud base that would cause an internal circulation and with more overall upward motion because of the instability from the radiative processes. So yeah, it's actually not, we've only done this with models to say that gravity waves are what starts the kind of depositional growth process. So that's where the updrafts are really weak. You have a lot of downdrafts too. Sorry, this is what the up and drafts look like. So you have more updrafts than downdrafts, but there's lots of updrafts and downdrafts. But overall, they make it a mesoscale updraft. And we've definitely observed this.
Okay, this question may be out of topic, but this peculiar curve, can you find this curve in like any observational evidence about this? Like, can you find with the Doppler radar network retrieval using that kinematics? Can you find this curve, or it is only for models?
Oh, I mean, we can absolutely observe the upward and downward motions. The gravity waves are harder. I think it's possible. I know in India, I mean, you guys have there's some good profilers, and a lot of people have done profiler work there, but yeah, to measure the gravity waves would be harder. I've thought of it. I've never seen anyone do it to measure the gravity waves from the convective to the stratiform region and link it to the observed vertical motions. It's an open question. One of you guys should do it.
Yes,
Or
yes.
talk to me about it.
Yeah. Okay, I have last question. So using GPM radar.
Hi. May I? Sorry, this is Vishal actually.
Yes.
I am kind of speaking from ICTS. So
Okay.
may I request the online participant to maybe wait a little bit longer in case we have time? We'll kind of come back to you. There are also a couple of other questions that participants have here.
Yeah, sure.
And I'll request, yes.
Sure.
Also, I'll request the people to keep questions quite brief so that,
Hello. Yeah, this is a nice talk regarding the observations. Especially, I was interested in the congested clouds that you were talking about, or land region. You didn't, I mean, like, you're saying that the tropical region, the congested clouds, the trimodal convection, the congested are mostly absent kind of a thing. But can we attribute to the characteristic feature of tropical regions where the low moist static energy around that 300 to 700 hectopascal, you have the low theta E values, and then this are a large surface heating. Can we attribute because of those things that the congested we are not able to see?
Potentially. Yeah, I always think of it more, and I think I heard most of your question. I always think of more of it as boundary layer driven, but there's also the shape of the cape, right? So if maybe that's kind of what you're getting at. So over ocean, the shape of the cape is going to be long and thin, and over land it'll be, which might, you have more low level fat cape that can then kick things off to make it go faster. So I always think of it as more of a boundary layer, but I'd buy that there might be some environmental, like moist static energy profile or cape profile that, yeah. It's this idea of this terminal versus transitional convection. And so people have studied this, but I feel like they've done it a lot more over the ocean and less over land. I mean, often things just go, you don't stay in the congested phase very long. So, yeah.
Yeah, why I'm asking is because when we see this cloud depth based on the radio sound observations for land, we could able to see the trimodal distribution, but the peak is very low. You know, the congested peak is very low compared to
Right.
the other two peaks. Yeah, it's corroborating with your result, but then, you know, just finding the mechanism.
I love that. Yes, that's great. And that's exactly what you all should be doing, thinking about the mechanisms of what might take you away from a paradigm that might only apply to ocean, but it might apply occasionally to land. That's great.
Yeah, hello. Thanks for the talk. Myself, Abhay. I wanted to ask about the cumulonimbus cells. You said that they prefer to be in a multi-cell system usually, and the life cycle of a single cell is usually 1 hour. So, what is the life cycle of a multi-cell system that they form usually?
Yeah, and I should mention it's not like they like to the multi-cell happen in low shear conditions normally. So like over Florida, we get them a lot because it's warm and moist and low shear. So the multi-cells are just a couple hours. So they're sort of in between an individual cell and then an MCS. So they might be anywhere from 30 to 50 kilometers wide. There might be a handful, you know, most of the time you only see a handful of them, so a couple hours. But yeah, I don't know. I have to think over it. Yeah, probably again over India. I don't know how often the multi-cells are observed. I just wanted to point out the convection can organize can organize as multi-cell, but it's not something I would consider a mesoscale convective system or very well organized, but that can affect life cycles of you know, when you only have a few cells. But that's a good question.
When we are looking at the anvils of the cumulonimbus, they're usually asymmetric. Is that due to the wind shear at the upper atmosphere, or are there other effects there too?
Yes, I think mostly this year, and that's something my group has done a little bit with, but again, and we've seen it very different. So like I think we see a lot less anvil over the Amazon than Darwin, for example. And then yeah, so I think shear is, but it's the upper level shear. So most people ignore upper level shear. They think about low level shear for convection, but I think this upper level shear is very important for both stratiform and anvil production. So yeah, that's a great insight. It'd be worth looking into more during the monsoons, for example.
Final question. You also talked about aged convective cells when you were discussing MCS. What do the aged convective cells entail? Like, what are they?
So it's instead of the fast moving convection, I mean, we all get older. But the fast moving convection will kind of detrain a lot of material, you know, the shear or just the movement of the system itself. But the aging cells that I'm talking about are the ones that aren't moving. There's not a lot of shear, they're not moving, and they're just kind of growing and dying in place. So it's really lack of either shear or lack of strong advective motion of the system, and then they grow and die in place, and that's when they just turn into stratiform. You put up the ice particles, they start falling as snow, they melt and cause the bright band. And so it's a very different dynamic than these kind of fast-moving linear systems. It's a great, I love, you guys actually listen, there's so many great questions on every aspect that I talked about. I love it.
Thank you.
I have a question regarding the trimodal distribution that you've talked
Mhm.
about. So you've mentioned the contrast between land versus ocean, but have there been subsequent studies like looking within an ocean basin, like east versus west? In the Western Ocean basins, you have higher sea surface temperatures compared to the east. Has there been like a difference in the distribution that people have observed?
Yeah, for the trimodal, not specifically. But what I showed was anecdotal. But not that I know of, but that would be worth a Google. But you're right. I think there would be east-west differences in the Pacific for certain. It'd be interesting in the Indian Ocean. You know, it's a very different structure than the Atlantic as well. So yeah, how the trimodal varies across the oceans is that's an interesting and between ocean basins and then across the larger basins. I think that's a good question.
Thank you.
Uh,
Yeah, go ahead.
yeah. So yeah, Courtney, thanks a lot for kind of staying awake for us. There are a couple of more questions, but I'm going to request people online as well as here to drop you an email. I hope you don't mind with the questions.
That would be great. I might not get them to them tonight because it's late.
No. We could wait. I mean, it's on email, so.
Yes, I would very much appreciate and I welcome questions. So more questions. And I think the group has been wonderful, and I really hope you have a good rest of your workshop.
Yeah, thanks a lot. Thanks a lot, Courtney. Yeah. Thanks.
Bye. Good night.